So what's the participant count that we're looking for? I'm just only seeing a few comments so far. How many participants have we got coming in?
We have a lot to register, but we can't estimate how many to join us.
All right, we'll give it another minute and then we might get started.
Okay.
Well, we've probably still got a few stragglers, but
recording in progress.
We'll get started now. First of all, welcome everyone to the latest edition of the Scientific and Industry webinar series. The series is co-hosted by the ARC EECEP Research Hub, the Monash Centre for Membrane Innovation, and the Membrane Society of Australasia. This week we have Dr. Zhongli Xi giving a talk to us on nanomaterials enhanced mixed matrix membranes for aqueous mixture separations. Zhongli is currently a research team leader and principal research scientist at CSIRO and has led more than 25 industrial engagement projects with a value of over $12 million. She has expertise in advanced membrane materials, processes for energy and environmental applications. She has published more than 110 journal publications with over 4,000 citations, 5 patents, 4 book chapters, and more than 30 confidential commercial technical reports in those fields. She is also a director of the Membrane Society of Australasia. Before welcoming Zhongli to speak, I'd like to remind you that please post your comments and questions into the chat function and keep yourself on mute while Zhongli is talking. We will have questions at the end. And with further ado, Zhongli, you've got the floor.
I'll share my screen. Okay, can you see my screen properly? And thank you, Stefan, for a kind introduction. And thanks everyone. It's really great honor and pleasure to present our work here. And I'm just hoping to share some of the work we've done in this mixed matrix membrane mainly for desalination and wastewater treatment for past nearly 50 years. And just a little bit of a background, I guess that's one of the reasons I have brought all of us together. And we know that energy and water has been top global challenges. And also we also know that efficient separation is really, really important. And it accounts a lot of like a very high capital and operating cost from costing economic benefit. And then so thanks to the advance of the membrane technology, membrane materials, and then so that we are all working on towards energy efficient separation. And there are a number of very well-known challenges in the membrane. And we always want to improve the flux, and we always want to keep the rejection property. And we know in particular for polymeric membrane, generally the trade-off effect between the flux and the selectivity. And also we know the membrane suffers membrane fouling. And there are many, many different approaches to working on that for different aspects. And then so nowadays, today I'm just want to share one of the approach, like a mixed matrix membrane, and utilizing the nanomaterials, and then in particular nanoporous materials, because it offers a lot of unique advantage. And we know the mixed matrix membrane has because it combines advantage between those inorganic nanofillers, and also it can, like say, combine the processability of the polymers, because in principle it's very easy to scale up, because we know the polymeric membrane and manufacturing process very well established. And also we can utilize the unique property of nanomaterials and then to achieve the desired high selectivity and also desired mechanical property as well. And for mixed matrix membrane, there are a range of nanofillers we could use. It can be either impermeable nanofillers like nanoparticles, zero-dimensional nanoparticles, or we could also use the permeable fillers like nanoporous materials. And then, but one of the key challenges, like for the mixed matrix membrane, is how to creating or how to form the uniform dispersion or homogeneity of the mixed matrix membrane. And then by achieving that, and then we can, like say, combining the features of both nanofillers and also polymeric membrane. And so just briefly, what we've done, sorry, just give me a sec, because I think my screen on my end. Okay, so yeah, just a little bit of what we do, like say, in this space. So we've been working on mainly from membrane materials and also up to prototype system. So we worked a lot on mixed matrix nanocomposite membrane. We have been exploring a range of nanomaterials, ranging from common silica, titanium dioxide nanoparticles. We also work on from 1D, 2D, or nanoporous 3D materials like a carbon nanotube, graphene oxide, MXene, or active carbon morph. And this, we really just look at how we can explore those property of the nanofiller to improve the flux, anti-fouling, or even anti-wetting property for a number of the membrane technology, membrane process. And we've been working on the flat sheet hollow fiber membrane fabrication, and we work on the module assembly. And we have in our lab, we have those flat sheet membrane. This is a very small scale, but the good thing that it can do the semi-automatic casting for flat sheet membrane, and also we have a hollow fiber casting facility as well. And then we can make it module, and also we make it spiral wound or hollow fiber, and then we can make the prototype system to do some demonstration. And then so we utilize the system to evaluate for desalination, water treatment, or organic water separation application. So today I just want to share a few membrane area we have worked in the past, I would say over 10 years, and then the evaporation, membrane distillation, and forward osmosis. So I'll start with the evaporation. Yeah, I'm not going to go through the evaporation, but I know we all know that. And so we start with looking at, like say, a very, very cheap polymeric materials. So we did a lot of work on the PVA polyvinyl alcohol membrane development. And the reason for that, because we know the PVA is cheap, and it has a very good film, the membrane forming property. And then, and also it's, we can synthesize in aqueous. So that's a green manufacturing process. But one of the big drawback is PVA is very unstable in water, in particular swells in the water. So in that case, it loses selectivity. So there are a number of ways to cross-link or to solving this problem. And then so we start this journey, we working on, by first we look at like a silica nanoparticles. And also we also utilize some common cross-linking agent. One of the cross-linking agents we have been identified is malic acid. So in this work, because we tried adding the silica, and we experienced a lot of agglomeration. So what we have done, like we utilize a sol-gel method to forming the silica oxide nanoparticle in situ, and then by that way we can form this organic inorganic bonding, and via this organosilicate complexing. And then, like say, there's a I just show a photo here because that one just shows the one on the right side. It's by utilizing, different cross-linking agents or different way to making the silica nanoparticles. And you can see the color is very dark. And that membrane or that film form is relatively brittle. And the other thing, and also that dark color indicating the silica nanoparticles dispersion, because for those two, they have same amount of silica content. But the one on the left is transparent. And then because that's indicating the size of the nanoparticles. So in this way, we are able to achieve uniform dispersion of the silica nanoparticles in this PVA nano matrix. And the other thing, we are able to suppress the swelling of the PVA. And then by doing that, and then we can achieve the enhanced of the water flux, and also we can maintain the high salt rejection as well. One of the reasons for that is because by adding or by tuning this, the silica nanoparticle formation, we are able to improve the fraction-free volume of the dense membrane. And also we are controlling the heat treatment, the temperature and the time during that membrane making process. We are able to optimize the membrane to maintain the hydrophilic property. So we also learn, how the silica content plays in this as well. And then, like say, because obviously when we have too many, because we're adding the silica oxide, and then it changes the membrane, the crystallinity, and also change the membrane surface property, like surface roughness, hydrophilic property as well. When we're adding the too many, and then we know, like say, because that agglomeration. So when we have those phase separation, we have agglomeration. It's actually there's a significant drawback for the mixed matrix membrane. And so we did a lot of optimization work, and then by adding this in the proper content, and then by changing the optimizing the fabrication method, we are able to tune its crystallinity and also the density and also surface property of this membrane. We are able to achieve the high water flux, and also we can achieve the high selection property as well. So we evaluate this membrane for both desalination and also for ethanol dehydration, because we know that for evaporation, one of the first commercial applications actually in the solvent dehydration space. So this is just one of the summary. We just compare with the other work. And we learned, like see, with the zero-dimensional nanofillers, and then we want to explore how those dimensional nanofillers affect the PVA membrane performance. So we started looking at like the carbon nanotube, and this one-dimensional nanofiller, because the carbon nano, we know it has a frictionless, the features. So if there's a chance for water going inside the carbon nanotube, it actually can speed up. It can facilitate water transport. And then we use the multi-wall carbon nanotube. So in this work, but we found out because carbon nanotube, commercial carbon, that one doesn't have any functional group. So when we're adding that one, so basically this is a purely just physical dispersion. So, and because there's a lack of functional groups, as you can see, so this is a swelling degrees indicating water uptake. And then as you can see, it's actually, because it's a physical dispersion, so actually this membrane itself still swells. And even it improves the water flux. And then, but I think for long-term stability, it's actually still happy because there's a phase separation. So what have done, we look at like the surface modifications. We look at like say, there's a carboxylic functionalized multi-wall carbon nanotube. And because we have this, the carboxylic functional group, so it is able to react or cross-linking with the hydroxyl group of the PVA and forming, that cross-linking. And also we're adding additional malic acid as a cross-linking agent to bridging this multi-wall carbon nanotube and also bridging with the PVA, so we can form in this dense cross-link network. And what we have been seeing, like say, for this functionalized carbon, we are able to improve the flux, and also we can improve the selectivity. And also, like say, in terms like the swelling, and it can greatly suppress the swelling. And then the water content angle is relatively, it's still increased by relatively, because this carboxylic group is a hydrophilic group, so we can maintain the, the content angle, also hydrophilic property as well. And then by further using the cross-linking agent, and then we are able to further increase the selectivity. But because of, it suffers with this reduced hydrophilic property, and then we also suffers, the water flux. So then there's a balance, and it's what we expected. So we want to optimize this because we know the cross-linking agent has some benefit, but how to improve further. So, and then we look at alternative cross-linking agent. So one of the cross-linking agents standing out is sulfur succinic acid. The reason we use this one, because this one has an additional sulfonic group. It has a hydrophilic functional group. And then so we're expecting by adding this, we are able to maintain the hydrophilic property of the membrane. And the other thing we did is we did the acid treatment of this carbon nanotube. And then to further improving dispersion, because we know that for mixed matrix membrane, and the dispersion is key. It's really a great challenge to be overcome to achieving the better performance. So for this work, and then the optimized membrane, which we have a, acid-treated membrane, and also we're using the sulfur succinic acid, and we are able to improve, enhancing the water flux, and also we can maintain the very high salt rejection. So we are breaking that, trade-off effect. And then we also look at a 2D dimensional nanosheets. So we start exploring the few nanosheets, and then the Maxine is one of them. So first, because Maxine also has the advantage of Maxine, it has a lot of functional group, but it's also swells in the water. And then, but the advantage, because we can utilize the interlayer spacing, because that interlayer spacing can provide a selective channel for separation between water and the other molecules, for example, the salt. And then, so first we look at how we can, to tuning this interlayer spacing, by using the malic acid cross-linking this with the Maxine. And then we are able to make this malic acid Maxine membrane. And then this is a XRD. And then for the dried Maxine membrane, it's pure Maxine membrane. We can see for dry membrane or the wet membrane, and the interlayer spacing change a lot, increase, because that's due to the swelling of that Maxine. But when we have this cross-link with malic acid, we can see we can significantly reduce that swelling. And then because of that, we are able to enhance the flux, and also again we're achieving very high salt rejection as well. And we test this membrane for real seawater, and then it maintains, for the laboratory running for 50 hours, and then it maintains very good performance. We also look at like the graphene oxide and utilize a similar approach, because graphene oxide, again, graphene oxide is even more easy to swell. And then so how to control that interlayer spacing is important. And then we have learned, using the sulfur succinic acid, we really just want to see how we can form in that thin film layer, and also forming this, flexible and graphene oxide framework to be able to achieve the efficient separation. And we evaluated this membrane for a range of the salt and the monovalent and divalent salt separation. And then the membrane itself achieves very high salt rejection, and that's one of, as expected. And also in terms of water flux, it's very high as well, because we did this at a very low temperature, close to room temperature, performance. And also we evaluate this membrane for alcohol dehydration as well for number of, the solvent. Again, this membrane has outperformed a lot of others. I think one of the reasons is really because we have been using that the sulfur succinic acid, because that has additional hydrophilic functional group. So we are able to enhance and maintain the hydrophilic property of the membrane, and then so we are able to achieve the better evaporation performance. And so from the learning, we have learned from this 2D nanosheet, because those work are proof concept study, and then we're using vacuum filtration to make a membrane. And so even the membrane is performing very well, but it's limited by the scalability. So, and then so we going back to study, like say, whether how we can utilize this, the nanosheets, and then to improve the, for the PVA membrane. So, and then so we have started exploring how we can make the ultra thin the membrane. So we have utilized the solution casting method, and then the aim is making the ultra thin the PVA nanocomposite layer on the substrate. So we spend a lot of time exploring, the various substrate or property of the substrate. And then we also spend a lot of time on how to optimize, how to formulate uniform, relative defect-free, the membrane. And then so we are able to, for this, we are able to achieve this membrane, which down to like less than 300 nanometers. So, and then because of that, we are able to, this membrane has achieved very high performance. But one of the reasons, again, because by having that maximum, nanosheets, and also having that sulfur succinic acid group, and then we, we are able to tuning the pore structure, in particular fraction-free volume, and then to improve the membrane flux. And also, because that additional hydrophilic functional group, it helps to maintain the hydrophilic property, which is very important for this PVA membrane. And this is this membrane performance. Again, we evaluate for some number of, the salt, and also we evaluate for number of the, alcohol as well. And this is a scalable membrane, outperform a lot of other membranes, and they achieve high flux and also high rejection, high separation factor as well. We also test this membrane for, because we want to know how stable this membrane. And we use both like a real seawater, and also we test for ethanol. We utilize 96% of the ethanol as a feed. And then for both, we run like say, a number of hours. But here I think when we mentioned about 30 or 50 hours, it's in a way, actually, it's not a continuous run. It's the actual running time is longer than this. For 50 hours, it could mean, let's say, 5 days. The reason for that, because we can only run the daytime, and because of our, the laboratory policies, so normally we have to stop during the nighttime. So the actual times, the membrane being evaluated is longer than the time stated here. It's just indicating the integrity and stability of this membrane. And then, so we know this membrane is stable. And then, so we just explore how easy to scale up. And of course, kind of is still limited by the facility we are having. But what we have done, we are able to scale up this membrane from initially just like say, the coin size, and up to kind of we are comfortable making the A3 size. And then using this, just semi-automated, just casting machine. Of course, this membrane will still go through a number of heat treatment nodes, a number of the post-treatment. But one of the, as the next step, so we are able to scale up this membrane. And then we are achieving that, because this membrane, we can just randomly take any of those, the thing and evaluate the membrane. This membrane has demonstrated, very good performance. And again, this is you can see the cross section. So we have this dense thin film layer formed on this porous substrate. And so next, I want to share some work we've done on membrane distillation, because we know that membrane distillation is emerging membrane technology, because it's due to its non-pressure driven and also thermal process. And then so we know that conventionally for MD membrane distillation is utilizing single layer hydrophobic macroporous membrane. So what we've done is, like say, we explore whether we can making the dual layer membrane. So the thinking, like say, we have those like a very thin we have the reduced hydrophobic layer. So instead we have a whole section of hydrophobic. So we replace part of a hydrophobic layer, a hydrophilic layer, because we believe have this, have a hydrophilic layer as a composite membrane. It has a advantage. We could lower the resistance to mass transfer because the water vapor transport length through the hydrophobic layer is going to be reduced. And the other thing, because we have this hydrophilic layer, and then we can reduce the conductive heat loss. So in that case, we can improve the thermal efficiency. And we have utilized the electrospinning technique to making this membrane, because the reason for that, because when we're using electrospinning, we can control the pore size, and also we can control the membrane thickness for both layers very easily. So we have been, we made the hydrophilic layer, and also we made the hydrophobic layer on top of hydrophilic, and also we made a hydrophobic membrane for the same thickness as a control. So, and also we compare with some commercial membrane here as well. And then to further improve them, because we know the nanofillers can have some enhancing effect. So we also added some active carbon. We add some, the nanofiller into this, mixed matrix membrane. So what we have found when we're adding the active carbon, and you can see this nanofiber, the morphology change, because then we have some extrusion. We have those, so that was spikes. So that extrusion of active carbon is actually helps to improve the surface roughness, and also because those protrusion actually it increases the water contact angle. So what we have been observing that the water contact angle has been increased, and then obviously if let us increase surface roughness, also increase surface area as well. And then because of the morphology change and also the surface hydrophobicity change, what we have observed, like the membrane performance, and the dual layer membrane with the active carbon has the highest performance. And then, like say, the single layer, it's it just fit into what we expected, and that one, because of enhanced the thermal efficiency, and also minimize the mass transfer resistance, so we are able to achieve the enhanced water flux. And this is just a picture to show we have different active carbon loading, and when we have a lot more active carbon, as you can see, obviously the color is getting darker, but also there's it doesn't mean the more is better, because when we add it too much, there's agglomeration happening, and it's actually a detrimental effect towards membrane performance. But the good thing that we are able to utilize the porosity of the active carbon, and then so that's why I say we believe for this, when the water transports through the membrane, it's not only that water can transport through the the macropores of hydrophobic layer, and also we can utilize the channel or the space between the active carbon to the polymer, and also in particularly if the water going through the the nanopores of active carbon, it can facilitate the water transport as well. We also look at because our group and the MAT team has been great expertise in morph materials. So because Sarah has such great expertise in morph, so and then we also look at how we can explore the morph in this space. And this is what actually I did with Stefan together, and we have specifically chosen our word because we know that a lot of morphs, they are not stable in the water. So we specifically choose a water stable morph. And also the other reason we choose aluminum fumarate because it's one of the cheapest morph and also has been scaled up using CSL's patented flow chemistry technology. And so in this work, we've been just explore how the aluminum fumarate is able to change the membrane performance. But in this work, actually, we found it quite interesting because it has aluminum in the morph. I said because of the metal there, it's actually electrospinning is not like as straight as we use an active carbon, non-charging particles. And then so we are forming this because beads on string structure. And this structure, it actually change the porosity, change the pore size of the membrane, and also change the surface roughness. And in this work, what we found, we are able to, I think the mainly, for the increase, enhancing the water flux. But this one, it doesn't mean this one is very good because this one still has some limitation. Because one limitation we found when we're using the morph for, we're making the nanofiber membrane, we found it's very hard for us to control the pore size. Because when we're using the active carbon, we can tune in the pore size because that's one of the, I would say, the advantage of using nanofiber or electrospinning technique. But for this one, we found it's very hard. I think because, as I said, we believe that's because related to the properties of morph. And then, so this membrane has a very high water flux, but has a problem in terms of, like, say, the wetting. So it cannot be used for if you have the water have some surfactant or solvent. And then we also explore, I'll talk about the wetting shortly, but I think we also explore, because we found that electrospinning seems to be the challenging. So we go back to the traditional, the phase inversion technique for making the hollow fiber membrane. So we added aluminum fumarate into the PVDF, and we made this using our machine, made the hollow fiber nanocomposite membrane. And then by controlling different loading, and then we are able to achieve the high water flux. What we believe one of the reasons we are able to enhance this water flux because by controlling this morph at the right content, we are able to increase membrane porosity, and that has advantage, or that has the effect to increase mass transfer. And the other thing, because the morph itself has different thermal conductivity, so by doing that, and also because of that increased membrane porosity, we decrease membrane thermal conductivity, and then we also achieve high thermal efficiency. So combining all of those things together, we have achieved high water flux. This is just showing some morphology for this aluminum fumarate morph PVDF hollow fiber membrane we made. And the PVDF show typical, we have the skin layer, and also we have the, the finger pore and the macrovoid, and also in the middle, we have some sponge-like voids in the middle. And then the PVDF itself is just, just very regular, those webbed structure. And then by adding the morph, we found actually change this structure. It's more like a linear, but it's disorganized, its structure. And then at a small, at a low loading of morph, we can see, or at least we don't observing that the morph agglomeration. So it's indicating it's relatively has a very good, distribution inside this PVDF polymer matrix. But when we increase, the morph load in particular high, like 5%, it's very easy to observe, number of areas we can see that the morph agglomeration. And that explains why the higher loading is not good. And we also, tested this membrane again for the real seawater, and also we evaluate this membrane for the anti-wetting as well. And then we can achieve probably 60% water recovery. So relatively adding the morph can improve the anti-wetting compared with the pristine PVDF. But we believe there's still more we can do because generally 60% water recovery is still not good, because when we're talking about zero liquid discharge, we really want to have a much higher, the water recovery. And so we start exploring the anti-wetting property of the membrane. We start with a composite membrane. This is a commercial membrane. So they have a PTFE substrate layer as bottom, but on the top they have polyurethane layer. And so this is the collaboration work I did with Dr. Jianhua Zhang and Stephen Gray, Professor Stephen Gray with Victoria Uni. And then so in this work, we have this polyurethane layer. It has about 20-30 micron thickness. It's a dense layer. When we testing the pore size distribution of this membrane, if we testing composite membrane together, we are unable to. We are unable to find out the pore size because our instrument limitation is down to like 50 nanometers. So which means it's lower than that. And then that bottom PTFE layer has a pore size of about 0.45. So it's very typical microporous MD membrane. And then so we test this membrane for anti-wetting properties. So what we've done, we just simulate, we just use a surfactant, the SGS, the very common surfactant present in particular, for example, textile wastewater. So we test this membrane, and then as you can see, for the PTFE membrane, obviously because of presence of a surfactant, and then those surfactant can lower the surface energy of the PTFE membrane, so gradually it wets the pore, and so the membrane will lose the selectivity, because this is just the figure here just show electric conductivity on the permeate side of the membrane. So we use that as an indication how good is the membrane's anti-wetting property. And as a comparison for this composite, for the polyurethane coated PTFE membrane, and then the membrane in terms say the anti-wetting property, because we can see the conductivity stays very stable. A reason we believe is because we have this hydrophilic surface. So that hydrophilic surface has a chance to absorbing. So basically that the hydrophilic head of surfactant can absorbing on that hydrophilic surface. So in that way we can improve the anti-wetting property, and also because we can prevent the hydrophobic layer to go through that. And we test this membrane for 100 hours actually. And then for this, we're adding significant 40 milligram per liter of SDS is quite a high concentration of the surfactant. And then as a comparison, you can see this membrane has demonstrated very significant, the anti-wetting performance. And this is obviously thanks to the dense hydrophilic layer. The data here we just show the normalized flux, because one of the drawback for this, because this one we actually sacrifice the water flux, because that thick layer of dense membrane, we are unable to maintain the water flux. So what we have been doing, we have expecting. So whether we can maintain that the hydrophilic layer, whether we can maintain the top layer thinner, because we believe once we have a thinner membrane layer, we are able to minimize mass transfer resistance. And then so while maintaining the anti-wetting property, and also we have a chance to improve the water flux of the membrane for the MD process. And then we did a lot of work and just making that the hydrophilic thin film layer. So we went back to the PVA because we learned a lot from the PVA membrane. So we're making this PVA-based hydrophilic layer, except we're using aluminum film rate morph. And then we have successfully made this thin film hydrophilic layer on top of this hydrophobic PTFE membrane. And what we have been observing is because we are making this thing, it's less than 1 micrometer thickness, and then we are able to improve the water flux. So not only like say we're maintaining water flux, we can even improve water flux, and also we maintain the high solid rejection. But most importantly, we are improving its anti-wetting property. So that is, we are very excited with this because generally, whenever we improve the anti-wetting, we always suffer with the water flux. But actually in this work, we are able to achieve in the both. And then we also explored, so since we've done in a flat sheet, and so whether we can do anything about the hollow fiber. So, and then we explored the hollow fiber member, but hollow fiber, we found a lot harder to do that because in terms, because there's a hydrophilic, hydrophobic, and there's a different feature of the surface property. Having that coating layer is very different, and in particular because we have been tried avoiding using solvent, we use an aqueous base. So we found that surface treatment is quite important, and also we explore different way of, we also utilize different methods to apply this hydrophilic layer on this hydrophobic hollow fiber membrane. And then, so in this work, we can form this hydrophilic layer after make the module. And then again, we demonstrate this membrane has, but obviously the formulation is very important because, this is different because the red color, this is just purely hydrophobic, that's a control membrane. But the other 3 colors, that's a different loading of the PV to gel ratio. And then, so by tuning that, the formulation, we are able to achieving a very high anti-wetting property. I think one of the reasons for that, because we have been modify this membrane partially hydrophilic. So if you look like, say, the water content angle of this membrane, because we measure the water angle on the shell side and also lumen side, because we modify the membrane on the shell side only. So if you look at the shell side, and it started changing from the hydrophobic down to the hydrophilic. And then, but we can still maintaining the lumen side as a hydrophobic. So, and then, but how much we want to modify that one, that's a key. And then, like I said, and also that change the LEP as well. So for the optimized membrane, we evaluated for the real leachate, landfill leachate. And then we are able to achieving the 90% water recovery, and the membrane still remains. But we didn't utilize any of the, the washing, back washing, or any cleaning in the process. So the membrane has maintained a very good performance, even for the 90% of water recovery. And this is original leachate. This is concentrated, and then this is the permit. And we did a full ICP analysis for both, in particular for this, the permit. It has a very high quality water. So actually, it's rejected, pretty much everything from the leachate. In this space, we also look at the integration of the membrane distillation with the other process. One of the work we did, with Shanghai Normal University, we just look at like how we can combine with DCMD with photocatalysis. I think because for this one, because we know the photocatalysis is very effective for textile wastewater treatment, and then in particular, if we explore for visible light, it gives more opportunity. And then, so in this case, we utilize their flower-like, bituminous based photocatalysis to photodegrade the textile wastewater. And then, but here we're using the membrane distillation for 2 reasons. So one is, we can help to separate the photocatalyst from that, from the water, so we can improve the recovery of the photocatalysis in the process to enable a continuous treatment process. And the other thing is like the membrane distillation can act in another treatment step because we can produce a clean water. So in that way, we can maintain the relative high concentration of organic in the feed, and then improve efficiency as well. And also we look at how we can treat in the real textile wastewater. And then because in one of the project, this is a Jiangsu project we did, and actually we're dealing with using membrane distillation for treating the textile wastewater. And then because we know the textile wastewater has a lot of surfactant, a lot of organics, so that's making utilize BCMD as a commercial membrane is very, very difficult because we have demonstrated a lot earlier, as mentioned, because the weighting is a big issue. And this is this is not using our dual layer membrane. It's just using commercial membrane. We just simply want to see how whether we can integrate the membrane distillation with some advanced oxidation process. And in this work, we have integrated with foam fractionation and also ozone. And the reason using the foam fractionation is it just should remove the surfactant. If you look at the pictures of the before and after foam fractionation. So the foam fractionation removes the majority of surfactant, but actually it doesn't have much with in terms of organic or color removal. And then, but the good thing, like after we done the foam fractionation, in terms of say performance, because of the removal of surfactant, so we can prolong the membrane performance. And then the other work we did, like say for ozonation, and the ozone has a different effect because for ozone treatment, and then so it's not only removing it removes the organic, including surfactant, but the most important because it also removes the color. So actually for ozone treatment, and then we can perform in terms of treatment efficiency, we can enhance the BCMD a lot better. So basically for this work, we are able to demonstrate, because we have running this textile wastewater. Again, we use a real textile wastewater. We are able to achieve near zero discharge. We have achieved water recovery of 98%. And then, like say, those two treatments each have a unique advantage. For example, the foam fraction, because removing that surfactant, we can improve anti-wetting, so we can achieve a high water recovery. And then the ozone, I think still need a further optimization. It providing opportunity to remove the degrade, the organic contaminant. But in terms of anti-wetting, because that depend on operation temperature, and then it still has the wetting issues. So the last one, I want to share some of the work of our for osmosis. I'll quickly go through this because I just realized that I'm running out of time. I'll probably talk too much. So for this one, we mainly look at for this, because we know when we're forming thin film composite membrane, the interfacial polymerization process is important. And then we explored the porous aromatic framework. For this one, we using a carbonized porous aromatic framework. So that one is forming the onion-like structure. It still maintains the high surface area of the puff, and then but it's more like a carbon-like structure. And then so what we have demonstrated in this work, we just say we don't need to add in. We just add in very, very tiny amount of this nanoporous material. We are able to dramatically improve the membrane water flux and also reverse solid flux rejection. And the reason for that, because if you just look at the structure, we are forming compared with the pristine membrane, we are forming a loose structure of the thin film composite. Again, adding too much is not a thing, because adding too much we have seen the agglomeration and also those structures started forming a defect. And then one of the reasons is because when we have those nanoporous material is affecting the interfacial polymerization, and then it making either it basically slow down the diffusion of NPD to KMC phase, and then regulating that IP process, forming the unique nanostructure. And also like we look at the maxing, so that one is adding, still making the nanocomposite. And then because we know the substrate plays, the important role as well for thin film composite. Again, when we have a surface treatment, and then it's going to affecting that TFC membrane. We actually, in this work, this is my postdoc, Dr. Xin Wu's work, we actually look at how we can forming that interlayer, maxing layer. So what we have done, explored, utilized the porous substrate. So we are not using conventional polysulfone or polyether sulfone ultrafiltration membrane. We're actually using a porous substrate. And then we adding this unique interlayer, the maxi interlayer, and then we regulating the interfacial polymerization, change the surface pore size, and then we are able to forming this maxi interlayer FO membrane, and with enhanced water flux, and also with reduced solid, the flux. And then the most important, because by using this technique, we can scale up, because we can make it the A3 size. We explore this membrane for not only for desalination, we explore for the suitable energy application. So we evaluate this membrane for CO2 capture system. I just briefly go this. I think really what I want to say for this slide, just to say, for the CO2 capture is very well known, but when you're using the NEA as absorbent, we need like some makeup that we need a trim cooler to providing the makeup water, and that one normally comes as fresh water. So what we are proposing, like we're using the FO process to replace the trim cooler to providing the clean water to this carbon CO2 capture system, and then basically expanding the cooling water sources. And we evaluate this maxing, the interlayered membrane, and then also in this work, this is still the proof concept studies. So in this work, we not only look at conventional NEA as a draw solution, and also we look at count the amino acid salt. This is mixed the absorbent, because that's the new compared with the NEA as an absorbent. What we have learned, this amino acid salt, the mixture has advantage of less toxicity, low volatility, and also high resistance to oxidation degradation as well. So what we found, actually this one's maxi membrane even show even higher water flux, and also high rejection when we use the AAS. And also we did some long-term stability for this membrane as well. And there's still a lot more to be done, because we found it as because it has a lot of other things. So that's why the water balance and then the temperature operating condition. So there's still a lot of work to be done in this space. But really, this one we just found it giving the opportunity. Actually, the FO could be utilized in this energy space. And the other work we did, this is for graphene oxide enhanced for osmosis membrane. We've been working with a local SME. I'm not going to go through the detail, but really I want just to say, again, by tuning this, the graphene oxide is nanofillers, we are able to achieve increase of water flux, and also increase, so by reducing, the reverse solid flux, we are able to achieve high selectivity as well. We evaluate this membrane for real seawater, and also we evaluate this one for real sewage as well. And this is from local wastewater treatment. And there's one of the advantages we can see is by utilize for the membrane which we made, compared with the conventional thin film, the nanofillers. And then the cake formation, the layer is significantly reduced. I just want to quickly show you, because I think what I want to say is, because we run some very simple, backwashing. We're just using the water as a cleaning, we run every 3 to 4 hours. We just washing with water for 15 minutes. But actually, I just quickly show you a video to see how effective in terms of cleaning. process. This is just the first minute of the cleaning, and you can see the yellow, the fouling layer. So basically after first minute, majority has been gone. It's very effective, and this membrane demonstrates has much better anti-fouling property. Okay, stop. I think with that, I'll stop my presentation here. There are many people I want to thank, and my colleagues and my collaborators. I'm not going to read through, but I really thanks a lot for your attention. I just realized I probably utilized too much of time. Thank you.
Thank you very much, Song Lee. It was a really insightful talk. We have a few questions in the chat. Declan, did you want to read your question out? I think you're first.
Yeah, sure. It was thank you very much for the presentations on me. In particular, the SEM images of the aluminium fumarate in the PVDF were just beautiful. Really great work. My question was, I'm just bringing it up now, relating to the multi-walled carbon nanotubes that you were using right at the start. You mentioned using functionalized CNTs so as that they could kind of like incorporate into the matrix. I had two questions about that. One of them was, did you encounter any issues with agglomeration? Because I imagine it's a relative, like there'd be a high-ish viscosity before it's cast. And yeah, I was wondering if agglomeration was an issue. And the second question was, is the orientation of these CNTs important to achieving like a high flux, or is a random orientation still sufficient to get high fluxes?
Thank you, Declan. I'll probably answer your second question first.
Sure.
I believe the orientation will be important because back to more than 10 years ago, I think we tried to make the carbon nanotube membrane by its own because we won't have orientated carbon nanotube. But in this work, we are not able to control the orientation of carbon nanotube. So my answer for this work will be no. And then back to your first question, it's carbon nanotube dispersion. It is very difficult, in particular in water. So we actually did use some sonication, and also that's why, I mean, having that functionalized group, right, it helps to dispersion. It helps, maintaining the dispersion for a longer period of time. And the other thing, that's the reason we introduced acid treatment on the later work. Again, that's to help to improve the dispersion.
Fantastic, makes sense. Because yeah, I guess that was great. I guess you can't really use surfactants if you're trying to get a very particular and pristine layer. Yeah, that was great. Thank you so much.
Thank you.
Regine, you also had a couple of questions. Do you want to call those out?
Yeah. Thanks, Domi. That's a really nice presentation. Learn a lot. I have some too many questions. With just the general question. So you mentioned you spend a lot of effort to select a good subject within membrane fabrication. Do you have any tip, like for this, like to select ideal subject within membrane?
I'm sorry, I think it's a bit broken. I think I missed your questions. And can you repeat, or Stefan, can you help me to?
Sorry, I didn't quite get through. Let me just check the chat.
Is that you mean the conductivity, right?
Yeah, conductivity is another one. And can you hear me now? And the other?
I'm just open the.
Okay.
Oh yeah. Okay, yeah. So that's right. Yes. Yeah. You mean the substrate? Well, the number of, like, say, the factors you need to look at, like selecting substrate, and then so first, obviously, hydrophilic or hydrophobic property. That's the first thing you probably want to look at, and secondly is the pore size, because pore size substrate is very important, and then, like say, I think that helps to rule out a few things already, and then I think we do have a lot of error trials, so yeah, because we found some of them, we thought, oh, actually that should be good, but after we doing that, we found experience of delaminating And also that's why, so not only the selecting the substrate, and also sometimes we probably do some pre-treatment of the substrate to improve that, the adhesion of the two layers as well.
Oh, cool. Oh, I see. Thanks. The next question is, I see there is a electrospinning to make a membrane. Is a flat membrane, and is that what the membrane size if you use this technique to make membrane?
We use electrospinning for flat sheet membrane. It's very easy to make in flat sheet membrane. And then in terms of the membrane size, you can scale up because that really depend on the machine. In our work, we can make it the A4 size, but there are facilities to make it even larger. But again, there are some other factors to be considered as well, because I think in terms of the evaluation work, it's very easy to be done. You can, but I think for scaling up, there's a lot more to consider because like a substrate, whether you use a nonwoven fiber or whether you have additional layer, all those becomes more important factor.
Oh, I see. And my next question is, I'm not sure for the anti-fouling and membrane swelling, are they the same thing?
No, it's not. And the membrane swelling study is more related to like how the membrane itself stable in the operation environment. In our case, mainly in aqueous environment. So how the membrane can maintain its pore size, can maintain the interlayer spacing. And then, but in terms of anti-wetting, it's more like how the membrane resists to the, organic foulant or surfactant present in the feed, in the treated effluent. So that's why for electroconductivity, really just we just look at it, how the performance. But for the swelling itself, we want to study wet swelling. We can just simply dipping the membrane into water, keep it for 48 hours, and then we measure how the membrane swells.
So by like just interesting by how can tell like the membrane swelling up to 48 hours.
For the PV itself, it can swell up to maybe double its size. So it's really depend on type of the membrane.
Oh, yeah. My last question is for preparation and membrane distillation, can this used for organic liquid separation besides desalination?
Preparation can be easily used for the organic water separation. For MD, we could use as well, but depending on what type of organic you are talking about, because for volatile organic, we might think a different configuration. Like, so we might use a sweeping gas membrane distillation instead of direct contact membrane distillation. Yes.
Okay, thank you. Thank you.
I'm cautious of the time. Did you want to quickly ask your question, and then we'll close the session after that?
Almost finished the time. Just a quick question. Only thanks for wonderful presentation. And the result you mentioned on using PCMD for textile effluent treatment, I noticed that you mentioned you have used the commercial membrane. But if you, I don't know, had any chance to use those optimized MD membrane which you have developed in the laboratory, have you had this chance to, I don't know, in the smaller scale setup to just use the same feed and compare the performance? And yes, what was your thought in terms of that, like ideal membrane for treatment of those feeds? Thanks.
Yeah, thanks a lot, Fazan, for asking this question. We did this, commercial membrane back to before the pandemic, so early last year. So at the time, back to then, our intention, like I said, we started using, commercial membrane to testing this, and then we moved to evaluate our own membrane with a new effluent. But the problem, like after that, since pandemic kicked in, where the company we had, right, that company is not able to provide us textile wastewater. So currently, I have the membrane, but I don't have the wastewater. So if any of you have the access to the real textile wastewater, please drop me an email. I'll be very, very happy to evaluate our membrane for real textile water. So that's the reason I use a landfill leachate, because that's one of the real effluent I can access. for later say.
Yes, really, pandemic was a
Thank you.
Thank you.
Well, I'd like to take this chance to thank Zhongli again for her really interesting talk, and thank everyone for attending. I'd like to highlight that we have another seminar in 3 weeks. Felicia will be talking about membrane fouling, and 2 weeks after that, Dr. George Chen will talk to us about organic acid recovery using membranes. The other thing to be aware of is that IMSTEC 2022 is currently underway, and I believe abstracts are either open or opening very soon. So keep that in mind. We're hoping to have everyone in person in Melbourne next year. So keep an eye on that one. Once again, thank you very much. Enjoy your day.
Thank you.
Thanks, Zhongli.
Thank you. Bye, everyone.
Bye.
Bye bye.